the topic digital camera. This image shows the image sensing pipeline. The image sensing pipeline is divided into three sections: camera body, sensor chip, and image signal processing. The camera body has three components: optics, aperture, and shutter. Optic will convert the scene to sensor. Whatever we are trying to capture, it will be sent it to the image sensor available in the camera, available inside the sensor chip. Then the aperture will control how much light passes through lens. It control how much light passes through lens. Then shutter represents how long the sensor collect the scene. It represents how long the sensor collect the scene. The next one is sensor CCD or CMOS. This is very important. It will convert the light into signals. Okay, on converting the light into signals, we are processing digital conversion, then we are getting the images. So whenever we try to capture an object, the light falls on the object, natural light falls on the object, those light will be converted into signals. This gain amplifies the signal. Okay, higher gain means we will get a more brightened image, lower gain means we will get a less brightened images. So after amplifying this, it will be passed through analog digital converter. Then we are getting the raw image. Okay, at this stage we will get the image. Then after that, we will perform some kind of processing to get the JPEG image. You can see the difference here. The raw image is somewhat less processed. JPEG image is much better one when compared to the raw image. Okay, so the demosaic represents, it interpret the color information. It interpret the color information available in this raw image. Okay, it may reconstruct the full colored images. Then denoise and shorten. Okay, this denoise means it will reduce the noise. Reduce the noise. Noise means something related to bad quality. Okay, so it reduce the noise and increase the image quality. Okay, it increases the image quality. Next one is white balance. White balance will adjust the color to make the image look natural. Okay, it makes the image to looks natural. It will adjust the color. Gamma curve, it used to introduce both brightness as well as contrast, which is suitable for human visual perception. Then compress we know will perform the reduction of file size. On performing all these operations, we'll get a image, JPEG image. Okay, so here we are going to see about two important sensors, CCD and CMOS, which was mentioned in the pipeline, right? So CCD as well as CMOS. So here I said earlier that a process of sensor is to convert the light into signals. Okay, so listen carefully. CCD is a very old kind of sensor. Most of the modern digital cameras use CMOS. Okay, so every light is converted into the signal. Okay, so each light will have photon. Photon is the building block of a light. Okay, so using photons only, we are getting a light, and the photon carries the light energy. Okay, so the photon is converted into the electron. Photon is converted to the electron when we try to convert the light to the signal. Okay, photon is converted to electron. Okay, each pixel, this represents the pixels. In case of CCD, each pixel will convert the photon to electron, which means light is converted into the signal in sensors. At the end only, the all the electron charges are converted into a voltage conversion. Why we need voltage? Why we need voltage means analog to digital converter can only take the input of voltage. So nothing but whenever a light falls on the image, the light is converted into electron. Electron is again converted into voltage. This will be given as the input to analog to digital converter. Okay. So in case of CCD, it is a sequential process. Only the last pixel can convert all the electron to the voltage. Each pixel will convert only photon to electron. finally all the charges will be converted into voltage here. But in case of CMOS, every pixel will convert the photon to photon to voltage conversion. That's what mentioned here. So in case of CCD, voltage is converted at only at the output node. But in case of CMOS, images converts the charge to voltage inside every pixel. Okay, so this is nothing but a sequential process. So at last only we are getting the voltage. In case of CMOS, every pixel itself directly convert photon to electron, then electron to charge voltage. Then it is given as an input to analog to digital converter. Analog waves are converted into digital waves. We will get a final image. The main factors affecting the performance of digital image sensor are mentioned here. We are going to see this one by one. First one is shutter speed. Shutter speed directly controls the amount of light reaching the sensor. So shutter speed represents length of time the camera sensor exposed to light. Okay, length of time the camera sensor exposed to light. Okay, longer shutter speed means we are getting more light, so the captured image will be more bright. So if the shutter speed is less, the image is exposed to less light, so then we are getting the less brightened image. So it is mentioned as overexposed or underexposed. Okay, based on the light only we are getting the brightened image or darkened image. The next one is sampling switch. It represents the physical spacing, nothing but a distance. Okay, it represents the distance between sensor cells as well as the on the image chip. Each chip may have different sensors, right? Okay, it represents the physical spacing between the sensor cells on the image chip. A sensor with small sampling pitch has a higher sampling density and hence provides a higher resolution. Okay, so then next one is fill factor. Fill factor is very important. It is nothing but active sensing area. Only the active sensing area can capture the light and provides the images. Okay, multiple sensing areas are there, but all the sensing areas are not active all the times. Okay, some may be useful for wiring, some may be useful for performing circuits. Okay, so the active sensing area, higher active sensing area, which is nothing but higher fill factors are usually preferable because they are they are one providing more brightful images. Then next one is chip size. Chip size is nothing but the physical dimension of the image sensor chip. The video cameras have traditionally used small chip sizes, but digital cameras use the film frame of 35 millimeter. When your device size is not important, it can be larger means you can have the larger chip size. So you may differentiate that our mobile phone is very low in size, but the DSLR camera or the professional camera is much bigger, right? So the whenever we are having a much bigger camera means the larger chip size will be there. So it can take the photograph in more fine quality. So if we try to reduce the chip size, the image quality will be reduced. Then analog gain. So before analog to digital conversion, the sensor signal is usually boosted by the sense amplifier. I said earlier in the image pipeline, right? So all the signals are amplified. Amplify is nothing but boosting. Okay, so boosting the amplified signal will be given to the ADC, and the gain is typically expressed in ISO. Lower ISO represents the cleaner images, higher ISO represents the brighter images. Brighter images may produce some noise also, not clean. Okay, lower ISO means cleaner images, the brightness may be somewhat less. Okay, then sensor noise. So noise, keep that in mind. Noise means it is not good, bad quality. Okay, we should reduce the noise. So noise can be from the various sources: pattern noise, dark current noise, short noise, amplifier noise, and quantization noise. In addition to that, some noise may be introduced by incoming light, exposure time, as well as the sensor gain, which was discussed in the previous. ADC resolution, the final step in image sensors analog digital processing is ADC, which determines the resolution in bit depth. Okay, we'll measure the voltage from the sensors only in bits. So 8 bit means it is 256 level, 10 bit means 1024 level, 16 bit means 65,536 level. All the camera usually may have 16 bits. So all the bits are not useful all the time. Only the usable bits are used to convert the images. So the usable bits are determined by using calibrating sensing noise or by performing SNR testing. Usable bits only used for converting the analog signals into the digital signals. So these are some of the main factors which we want to know in digital camera. And digital post processing is that after digitization, the digital signal processing in the last phase we have represented, right? Demoising, white balance, gamma correction. It will be happen to enhance the images. So the next topic is sampling and aliasing. So sampling is nothing but the process of converting a continuous signal into the discrete set of value. So imagine a car or a train is moving fast. Okay, if we try to capture the image, what we are trying to do, the continuous moving one is captured into a static one. Okay, a part of the moving is captured in your image, right? So we are trying to convert the continuous into a discrete. Okay, the car is actually moving. I captured an image, so this point is captured. Okay, so whenever I try to capture this place, this point is captured. So I'm trying to convert the continuous process, continuous signal into the discrete set of value. So aliasing means whenever the high frequency signals or high sampling images are captured, we may not capture exactly, right? So if you try to capture a static one or stationary one, we'll get exact same image, right? But if you try to capture the fast moving train, the image may not be captured correctly. So that is called as aliasing. The exact details may not be obtained correctly. So the aliasing bad one. We have to avoid. We want to avoid aliasing in order to process the image further. Okay, so that's what mentioned here. Aliasing happens when the sampling rate is too low to accurately capture the signal variations. The car or the train is moving very fast, but we are unable to capture with high frequency. Our sampling rate is very low, so aliasing happens. Okay, so here we have represented a few signals, right? So the above diagram represents the two sine waves, one at frequency f equal to 3 by 4 and other at the frequency f is equal to 5 by 4. This blue wave represents the frequency 3 by 4 and the 5 by 4 represented in red wave. Whenever the two sine wave meet each other, the point is mentioned here in black lines, right? Whenever the two curve meets, then we have represented a black line, and both the waves are sampled at the frequency f is equal to 2 and it produces the result which is shown in the right side of the diagram. Now you see here, after sampling at frequency f equal to 2, we are getting both the waves. Okay, now you see here, again the blue wave represents 3 by 4 frequency and it represents the 5 by 4. Two sine waves are here. Then we have performed the frequencies sampling of 2. Then you can see that the same point, right? Both are in parallel one. Okay, this is parallel. Again, this is parallel. This is parallel. The sampling point is same in both the waves. Okay, sampling point is same. Okay, you can see the difference here because this is not in the same point. Okay, this is not same. This is not same. Okay, the aliasing of one dimensional signal is represented in this image. Okay, so in order to avoid aliasing, we must perform filtering. Before that, if you don't sample fast enough, the high frequencies get misinterpreted. So this is a very important formula, Nyquist frequency. Okay, Fs is greater than or equal to 2f max. This is the minimum sampling rate required to reconstruct a signal without aliasing. If this condition is matched, then we won't get aliasing. Okay, the frequency Fs is greater than or equal to 2f max is represents the Nyquist frequency, and Rs equal to 1 by Fs represents the Nyquist rate. This four image shows the filtering as well as aliasing. This is the Original full resolution images. So you may see a fine patterns here. This is the original image. So if you try to capture this image means you may get the exact right image, or sometimes you may get an image like this. So this is aliased image. Okay, so this have higher sampling rate, or having very fine detail, it have high frequency. So when you try to capture, you may not get the exact fine details. You could see the difference here. Some of the patterns are changed. Okay, this checkerboard patterns are changed. This is not actually right. When you try to process the image, assume it is an x-ray image or some image related to medical processing, means the brain tumor or any kind of finer details is required to process. But if you try to process this image, we may get the wrong result. So aliasing is very bad. We have to overcome the alias. So we have to keep only the correct details. Okay, in order to keep only the correct details, we are performing filtering. Okay, this is 25 percentage of fixed filtered box. This is 100 percentage filtered box, and this is a high quality filtered box. The filtration, this part is completely removed. Okay, instead of getting the wronger pattern, we are completely removing to get only the right patterns. So this part alone is right. Okay, so the aliasing is bad. In order to overcome the aliasing, we are performing filtering. The filtering keeps only the correct data. The false patterns are removed. The next one is point spread function. Okay, imagine a star in a night sky, and it is a perfect point in a space, right? When your camera takes a picture, the point doesn't appear as a single picture. Instead, it appears as a blob. Those blob is called as a point spread function. Okay, it describes how a single point of light is spread out or blurred by the system, which is nothing but the combination of blur introduced by the lens as well as by the area of the chip sensor. Okay, so here we have two images. The first one represents the blur caused by the optical system. The right side image represents the Fourier response of the same plot A. Okay, the wider rectangular function in the plot A, the wider, this represents the rectangular function. The plot A represents the rectangular function used to represent the PSF. The wider the area, if the area is wider, then we can say it is more blur. If the area is narrowed, then it is less blur. The vertical axis represents the intensity, and the horizontal axis represents the spatial dimension. The spatial dimension is converted into the frequency domain. Okay, so this wider area in a plot A is narrowed in Fourier transform. Okay, you could see that wider area is narrowed. The narrowed area is broad. Okay, when you try to convert the spatial dimension to Fourier transform, Fourier frequency domain, you can say that a narrowed one is broader, broader one is narrowed. This is used to just understand how the aliasing happens. Okay, it doesn't represent the cause of the aliasing. The same image, but with twice the pixel spacing is represented. Here, previous image represents half this pixel spacing. Here it represents twice this pixel spacing. Somewhat the space alone is enlarged. There is no change in that. So whenever you try to increase the broaden the spacing, the curve will be somewhat narrowed. When you compare to the previous plot C, sorry, plot B, we get some narrowed plot in D. That's what about PSF. So remaining part will be continued in next video. Thank you.